Welcome back, Outsiders. This is the next part of our land navigation series. In this video, we're going to deal with directions, which includes that nasty thing called declination, distances, which deals with mostly map scale, and also designations, the way things are labeled on a map. If you missed the first parts of our series, in part one, we went over all the important information in the margins of the map, contour lines, and how to read those contour lines. In the second part, I went through a tour of Zoar Valley showing all of those topographic features in real time. And then in this video, we're going to go over the final 3 Ds of the 5 Ds of map reading. Let's dive right in. In previous videos, I mentioned the book called Be Expert with Map and Compass, the Complete Orienteering Handbook by Bjørn Kjellstrøm. It's a great resource, and I really like the way he goes over the 5 Ds of map reading. In the first 2 videos, we went over descriptions, which is all the information in the map margins and what that means. We also went over details. Details are icons, contour lines, and we went over all of the different topographic features that can be formed using contour lines. In this video, we're going to go over directions, distances, and designations. So what we have here is what's called the compass rose. And you're probably familiar with the cardinal directions: north, south, east, and west. And I like to remember how to orient the compass based on the word we, because then we always know that north is up and south is down. Then we have what are called the ordinal or primary intercardinal or intermediate directions: northeast, southeast, southwest, northwest. Those are pretty easy. But now we're getting into what's called the secondary intercardinal directions, a little more complicated. This is what's in between now. We have our north-northeast, we have our east-northeast, east-southeast, south-southeast, and so on. Then we have these things called azimuth and bearing. A bearing is the number of degrees from one point relative to another point, whereas an azimuth is the number of degrees measured clockwise from north, with north being either 0 or 360. So as you can see, the numbers go clockwise around the compass rose. So an azimuth of 45 degrees is the same thing as a bearing of 45 degrees east of north. And that's written like this: 45 degrees east of north. We can also say an azimuth of 135 degrees is the same thing as saying 45 degrees east of south, written like this: 45 degrees east of south. And we can take a look at a typical compass, and we see we also have our cardinal directions: north, south, east, and west. We have the ordinal or primary intercardinal or intermediates: northwest, northeast, southeast, southwest. And we can also see we have our azimuth going clockwise around from north. You can see the degrees increasing clockwise, and remember, north is either 0 or 360. Then we have something called declination. And if you recall, back in our first class, we looked at the map margin and we saw a declination in the map margin. Now let's take a closer look at what that actually is. So we have these arrows, and we also have this star. And we'll learn that this is abbreviated magnetic north, this is grid north, and the star is usually considered what is called true north. But which way is north? Good question. So looking back to our 6th grade model of the Earth, We remember that the latitude lines are going horizontal, the longitude lines are vertical, and what's important to look at here is these longitudinal lines, no matter where they are, they're converging on this point right here, and that's our North Pole, and we call that true north. It's important to note that this is also called geographic north or map north, and that all maps are laid out with true north directly on top. Almost all maps. We'll get to that later. Here we have magnetic north, and think of the Earth as a giant magnet. The shape of the Earth's magnet is roughly the same shape as a bar magnet. Notice that this is the North Pole here, but it's the South Pole of the magnet. The magnetic field is actually reversed. And the Earth's magnetic field is inclined about 11 degrees from the axis of rotation. So there's about an 11-degree angle right here. And you'll usually see magnetic north abbreviated with an M and a lowercase n. Finally, we have what's called grid north. And you can't see them really good on here, so let me highlight them. These are our UTM grid lines, if you remember back from our first class. And if you see, these are all oriented to north, or true north, or oftentimes abbreviated as grid north with a capital G and a lowercase n. A good way to visualize this is looking at it on a map like this. We have our North Pole, here's our grid lines. We have our grid north, and our true north is up here. And then our magnetic north is pointing over in this direction. This angle is what's called declination. Remember, these grid lines are all converging on true north. So if I go back to here, think of this grid line actually converging. If we actually had a three-dimensional model like a globe, those lines would actually converge on the North Pole. But maps are flat. Here's just another way to think about that. Our North Pole is our true north. We have our magnetic north, and these are our grid lines on our map, and see how they're all converging on the North Pole. So if we're reading the map with our compass, we need to account for this difference. This is one of my favorite diagrams for trying to understand declination in the United States and the magnetic field in the United States. We see this red line right here with a declination of 0. What that means is if we were at that location, we wouldn't have to worry about declination. And I like to think of this as roughly the Mississippi River. So if you are east of the Mississippi River, you have what's called west declination, and this is a negative declination. If you're west of the Mississippi River, you have what's called an east declination, and this is a positive declination. And here are some examples of some declinations you may see in the field. Acadia is east of the Mississippi, therefore it has a west declination, and it's a negative declination. So we have a 16.3 degrees difference between true north and magnetic north. If we're at the Great Smoky Mountains, we're still east of the Mississippi. However, we're a little bit closer. So our declination is only 6 degrees there, still negative, and you can see the difference between true north and magnetic north. Now, if we look at Mount Rainier National Park, which is now on the west coast, we have a 15.6 degree east declination, which means it's a positive declination. So what do we do about this? There is a mathematical way to figure out declination, adding and subtracting depending if you're going from a map to a compass reading or a compass reading to the map. I'll get into that in another video. My suggestion is just to buy a compass with a declination adjustment. This is a Sunto compass, and it has this key, and you just adjust the declination on the back side. So why do we care about declination? Well, it depends on how far we're going to travel and how we're using our compass. If we're off by just 1 degree and we walk 3,000 feet, we're going to actually be off by 50 feet. Now, multiply that out. Let's say that we are off by 10 degrees. So after walking 3,000 feet, I'm going to be off 500 feet if I don't set my declination. I'll be off almost 2 miles after walking 10 miles. So it can add up really quickly, and set you off course very, very quickly. So it's important to set your declination. Now, if you're just on a very small trail and you just need to know north, south, east, or west, whether you need to make a right turn or a left turn, declination doesn't really matter too much. I have a bunch of different maps from different manufacturers, and each one of them shows declination in a little bit different way, but they all show what your declination is. And it's important to set your declination before you hit the trail, because you don't want to be doing this on the trail. So let's first take a look at the Adirondack High Peaks map. And if we take a look at the way they have it designated, we find the legend, and in this bottom left-hand side we have a 14.3 degree magnetic declination. We see the magnetic north, we see a star, which is our true north, and then we have GN, which is our grid north. Next, let's take a look at our White Mountains trail map. This one does it slightly different. This one only has magnetic declination in 2017. The date is always important. And it just shows true north and 15 degrees west declination. So we would set our compass to 15 degrees to use this map. Next, I want to show you how the National Geographic maps do it. I have a couple of these. I have one of the Adirondacks, one of the Catskills, one of the Great Smoky Mountains. They all do it very similar. It's a pretty cool way that they do declination. So if you open up the map, you're not going to actually see it in the map legend, but if you take a look at the actual map, there's this printing on this map, and it has a compass rose that's oriented to grid north, the star above, and then it actually has a scale model of your compass where you can place your compass on top, place it at grid north, and then adjust your declination to fit over the magnetic line that they have here. And it does say approximate declination of 14 degrees 30 west in 2012. This is a really good way to double check that you're orienting your compass declination to the map you're using. And finally, I alluded to it before, not all maps are drawn to true north. There's one exception that I've come to is orienteering maps. And this is an orienteering map that is local to my area, Chestnut Ridge, where the Eternal Flame is. And if we look, it says the meridians are drawn to magnetic north. What that means is the grid lines on this map are actually oriented to magnetic north, not true north. So you would make your compass declination 0 degrees in that case and use that because they've already done the adjustment for declination with the grid lines on the map. So now we're going to look at how we determine distances on the map. And first we have to understand what the map scale is. And the map scale is usually given in one way or another in the map margins. And what you need to remember with map scale is large is small and small is large. It's a little bit counterintuitive, but you'll see why. Map scale is usually given in a ratio. In this case, it's 1 to 24,000. And what this means is 1 inch on the map equals 24,000 inches in the real world. And a ratio is a fraction. So we can rewrite this as 1 over 24,000. If we take a look at two common map scales, 1 to 24,000 and 1 to 62,500, and if we rewrite these as fractions, we see that it's 1 over 24,000 and 1 over 62,500. And because these are fractions, 1 over 24,000 is actually bigger than 1 over 62,500. So this is called a large map scale compared to a small map scale on this side. Map scale is shown in one of 4 ways. One way is the ratio. We see it as 1 to 12,000 there. 1 inch equals 1,000 feet. and we see scale of 1 to 24,000 there. Then we look at different rulers, and they can be divided into miles, kilometers, and even feet and meters. So how do these ratios relate to the territory on the map? When we say it's a small scale map, which is the 1 to 62,500, it shows a larger territory with less detail. Then as we get to progressively larger scale maps, so here's 1 to 24,000, 1 over 24,000 is a larger number than 1 over 62,500. So this is a large scale map compared to the small scale map of 1 to 62,500. This map shows less territory, however, it's going to show more detail. And finally, we have our largest scale map, 1 to 12,000. 1 to 12,000 is a larger number than 1 to 24,000, which is a larger number than 1 to 6,500. This map is going to show the least amount of territory, but the most amount of detail. If we take a look at an example of these maps, what we're looking at here is the 1 to 62,500, and you can see not a lot of detail in the trail that we're looking at, but it shows a large area. Then if we go progressively to our next map, 1 to 24,000, now these maps are scaled to be printed on an 8.5 by 11 piece of paper. Now we're seeing less of the trail, but a little bit more detail. Notice here's Carpenter Road and Humphreys Road here. Now if we take that last map, 1 to 12,000 scale, now this is our largest scale map, so it's going to give us the least amount of territory, but the most amount of detail. So you can see that you can tell a lot of switchbacks and a lot of detail in this trail map that you couldn't see in that same area right here. So this is just a table of some common map scales that you're going to encounter. And what I did is I bolded the common ways that you use them. So a 1 to 20,000 map is typically used with centimeters and meters because 1 to 20,000, very conveniently, 1 centimeter represents 200 meters. Similarly, a 1 to 24,000 map is conveniently used in feet because 1 inch represents 2,000 feet. Kind of an older version, the USGS used to have them in this format, was the 1 to 62,500 because 1 inch approximately equaled 1 mile. So designations are pretty easy. It's the labels given to various topographic features on the map. And there's 3 kind of simple ways that cartographers label maps. Each map might have its own theme, but typically you'll run into these 3 rules. Number 1 is corresponding colors. And if you remember the map colors, blue was water features, black was buildings, brown is contours, and so on. So you'll see those various map features labeled in those colors. You'll also see regular type for place names, boundaries, man-made objects, and you'll usually see italic type for any kind of water features. So let's take a look at this map and kind of point out a couple of those. Let's look at the easiest one, the Genesee River. So we see that that's labeled in blue and in italics. We also see some waterfalls, also labeled in blue and italics. Then we take a look at the different ways this map has man-made things labeled, like Portageville is the name of the town. It's got its own typeface. And then each street is labeled in black and regular typeface with some sort of theme showing the size of the roads in different typeface. As you can see, Portage Street's a little bit bigger than Pike Street, which is a little bit smaller. So we've gone over all 5 Ds of Bjørn Kjellström's 5 Ds of map reading: description, details, directions, distances, and designations. These videos have been the perfect primer to get ready for the next part of the land navigation series, which is using a map and compass. So I hope you liked this video. If you did, be sure to click that like button. If you want to see the rest of the land navigation series, any new videos that pop up, be sure to subscribe to my channel. That's it for now. I'll see you guys outside.